Good afternoon, everyone. A very warm welcome to all of you for joining us today for this exciting session on Meet the Mind of AI, LLMs Made Easy. This is brought to you by L&T EduTech as part of our weekly masterclass series. So before we dive in, I will just tell you a little bit about our masterclass series. It has been designed to deliver industry-relevant knowledge to students, educators, and professionals, both from academia and the industry. So every week on Wednesdays at 3 p.m., you'll be able to hear from tech leaders and innovators on trends that are reshaping our world. So go ahead and block your calendars and join us for 60 minutes of expert insights every week. Before we move ahead, I hope that I'm visible and the audio is clear to all of you. If you have any problems, please just raise your hands and we'll do our best to get things sorted out for you. Um, so, yeah. And today's session is particularly meaningful as there is no better time to kickstart a conversation on one of the most in-demand topics, which is artificial intelligence. And today we are going to be talking more about large language models, which is the mind behind things like ChatGPT, Claude, Gemini, and so much more. We'll uncover how they work, where they are used, and why understanding them gives you a serious edge over others in the competitive job market. So get ready to explore, have your questions ready, and because the future of AI is going to start just right here. Now, let me just introduce our expert to you. Our speaker for this session is Mr. Srinivasa Koushik, IT practitioner and AI expert at L&T EduTech. With over 23 years of global experience, Mr. Koushik has worked across the domains like IT, analytics, augmented reality, CAD, and so much more. Transformation across sectors, including manufacturing, aerospace, and defense. He is an alumnus of Singapore Management University, holding a master's degree in data analytics and machine learning. He brings both technical depth and practical insight, a rare combination that makes him the perfect guide for today's topic on large language models. Before we dive in, I request the participants to please drop your questions, anything that you may have in the chat box, and we'll take up the questions in a live Q&A towards the end of the masterclass. So now let's dive in. Over to you, Mr. Koushik.
Thank you, Tina, and good afternoon to all. I hope I'm audible, Tina.
Yes, very much.
Let me just share my screen, and you can tell me if you're able to see the PowerPoint presentation clear. Are you able to see the first slide clearly?
Yes, sir, it's fine.
Okay, let me also do a bit of toggle and see. You're able to see a fine web
Yes.
site?
Yeah.
Okay, great. All right, thank you, Tina, and a warm welcome to all of you. Thanks for joining in. So, as Tina mentioned, the idea of today's session is to talk about LLMs. And in a short span of, let's say, less than an hour, the objective from my side is to see how we can make certain things or demystify certain things that the jargon around LLMs, like you have GANs, you have RAG, and then you have LLMs. And what are these models that are being used by ChatGPT, DeepSeek, and so on and so forth. So I would like to mainly go to the core of these and then use some common parlance and then address those terms and terminologies so that you get motivated and you understand what the motivation behind these LLMs is. So without further delay, let's get started into the world of LLMs. So the main agenda today is I'll be going through 3 steps which are the core behind the creation of LLM models. The first one is called pre-training. Then the next one is post-training, but post-training has 2 stages. One is fine-tuning, the other one is reinforcement learning. You might have come across this fine-tuning LLMs term quite a bit in social media and YouTube. Then we go to reinforcement learning. So if you can see the definition there at the bottom of the slide, LLM is nothing but a statistical language model. So it's trained on massive amounts of data, as we will see. But the key word to note here is that it's statistical. So it is not, it is still stochastic. It is still, there is some room for certain improvements always. And over the last 2 years, it has improved drastically. And I'll also show you towards the end where it is some of these models are lacking. So the first step, as I told you, is pre-training. We will go through pre-training in as much detail as possible. So what happens in pre-training is that if you ask me in one line, we just try to compress the entire internet, the knowledge on the internet, and get it into one place. So we gather data from internet and we build the text model or the base model, it's called. That is the objective of pre-training. So, okay. So let me just go and show you the website, which is the website. Okay. So let's start with this website. So this website, which is from Hugging Face, is called, Fine Web Dataset. What happens here in Fine Web Dataset is that the entire internet sort of is crawled by a crawler called Common Crawler. Again, it's an open source crawler. It crawls. How do we crawl? We go to a website, let's say, and then there is a link in the website. You click on the link that leads you to another website with multiple links. This crawler goes into all those links and tries to get all the data from there. We clean it up and then we arrange it, organize it in bunches, as you can see here. You can see here technology data is grouped here, accommodation is grouped here, photography, scholarship. There were trillions of words or text. So the objective is to gather all the text, clean it up, and bunch it in logical groups. That's what Fine Web has done. This belongs to Hugging Face. So all the models out there, major organizations, have an equivalent of the Fine Web along with them. So I just wanted you to take a look at this. You can explore it at your own leisure. So if you can see here at the bottom of the slide, I mentioned 15 trillion tokens of cleaned and deduplicated English web data, which means that almost so many words have been scanned and then organized into this data set. Now, the first step is to download and process the internet, like I told you. So we get as much text as possible, and then we try to make it as high quality as possible. So these are the steps. If you take Hugging Face, these are the steps that are followed by Hugging Face. Let's take this as an example. The first step is URL filtering. So what we do typically is there are some unwanted nasty websites which we don't want to see or get recorded. We filter that out. We then extract text. We just remove all the markups. If you have seen the typical HTML markup, start, end, tag with slash, all that is removed, and we are interested only in the words and text. Then what happens is language filtering. Language filtering is nothing but if you are working on English language dataset, then all the websites that you're crawling through have to be majorly English based, at least 80-90% English based. So on and so forth. It goes through many steps. And then finally, we also have to filter out the personal information, which is sensitive, and that is also filtered out. So this is the entire pipeline by which the fine web data set is captured. And what is the result of this capture? Like I told you earlier, if you remember, we have to get all the data, all the text from the internet, because LLMs work on text, like you know, and further they convert it into digits. We will see that later. But this is how it looks like. This is a small snapshot of the entire data set that's there. If you can, imagine this another billion times or million times, that's the amount of text that's there. The objective is to make this one-dimensional sequence. What do I mean by one-dimensional sequence? Here on the screen, you see a length and breadth. It's two-dimensional. But of course, this is the equivalent of the one-dimensional set. So imagine this as a long sentence starting from the first word says a key factor in how LLMs, and then an endless one-line sentence. The objective is to capture the entire thing as a one-dimensional data set, sequentially arranged. And we humans think in words, but the machines think in numbers, or in terms of, if you go finer, it in terms of voltage levels, zeros and ones, which is called bits and bytes. So this entire text that I showed you, which is captured by crawler, is converted into raw bits. Bits are nothing but zeros and ones. I think most of you will be familiar. So we have, if you see here like this, we have 2 bits repeating over long sequences. It's just zeros and one, zero and zero and one repeating for miles together. So how do you make sense out of this? How does the machine make sense out of this? So we need to get the objective is to get a combination of more bits and shorter sequences. What do I mean by more bits? For example, 1011 can be considered as one chunk. The next four can be considered as one chunk. So instead of 8 bits, we have two pieces of information now. That's how we make this shorter and we look for patterns. So the objective, like it's mentioned there, is to have more bits and shorter sequences. So you can look at an example here. For example, 000, 10, 100 is the binary equivalent of decimal 20. You would have seen number systems like decimal, hexadecimal. So these 8 bits now become just 20. Imagine that entire text that I showed you is converted into 20, 356, 540, 200, and all those things. Then the entire text is shrunk into few numbers rather than zeros and ones. Now we compress this. Now, further, what we do, if you see in this slide, I've highlighted, let's take the sequence shown in the second line, 30, 45, 23, and so on up to 251. You see two repeating patterns of 30 and 45, again 30 and 45 repeats. Now, what if I combine 30 and 45 highlighted in yellow to a single number, and again 30 and 45 highlighted in yellow to a single number? So this entire sequence is reduced by two numbers now. Now, this process is repeated often till we arrive at a smaller set with bigger numbers instead of zeros and ones. So if we take the example of Chat GPT, like I've written there, it uses 100,000 unique tokens. The vocabulary of Chat GPT is 1 lakh. To be precise, it's I think 1,00700 or something, but roughly about 100,000. So, but it is trained on trillions of tokens. So what does this mean? I have trained on trillions of numbers, like I showed you, or tokens or words, but if my vocabulary is only 100,000. So to intuitively understand this, let's say you read 10 books. You would have, in your lifetime, you would have read 30, 40 books, but your English vocabulary will be only 1,000 words, right? So it's the equivalent of that, because how ChatGPT or these LLM models think is that ing will be a particular token sequence, let's say. If you have done NLP, if some of you have a background on an natural language processing, then we do this stemming, lemmatization, and all that and truncate. If you have running, jogging, thinking, all end in ing. So that ing is stemmed out, and that ing can be a single, vocabulary. But you have read ing 3 times in running, jogging, walking. So three tokens, but then one vocabulary word. So that is how this whole thing is shrunk and optimized from the internet. Now I would like to show you a sample of how these tokens look like in the real world. This tick tokenizer is a site which is open for all, developed by OpenAPI. I'll just toggle to the website. So I'll be toggling during this session between websites and my PPT. So kindly bear with me. So let me go to this tick tokenizer website. Yeah, this is the actual website. Now I've pasted a text here. If you see, I've just for our session, I've pasted the definition of LLMs there. Interestingly, if you see, when I hover my mouse over the LLMs, see, how do we humans think? We think LLMs is a plural of large language models, abbreviated LLMs. But see how the machine has captured it. LL is equivalent of 4178. If you can see at the bottom box, when I highlight LL, it highlights 4178. When I highlight MS, it highlights 22365. So it doesn't understand LLMs the way we understand. What is easier for you might be difficult for the system model, and what is easier for the model might be difficult for us. So this is a very good website. I'll share the link later. Maybe you can play around with this and see how Tick Tokenizer works. This is developed by OpenAPI. And this is how the entire text is tokenized. See, the text that I pasted on the top left box is converted into bottom right box. This is how the system looks at it. Okay, I'll toggle back to my PPT. Yeah, good. So now the step number 3. So what we did so far, we shrunk the entire website into numbers of bits. Then we did tokenization. Now step number 3 in pre-training is we are going to do neural network training. Now, if you have a background on neural networks, fine. Otherwise, I'll try to keep it in common parlance so that for the benefit of all. Now, what I've done here is highlighted NLO. I've taken a chunk from the tick tokenizer that we saw. I'll just show you. 527. If you see at the bottom, I highlight 527 16572 389 6908. These are the 4 numbers I put there. So the next one has to be 30525, the equivalent of data sets text on the top box. So it has to predict 30525, as you see in the right hand side, the dull green box. This is what has to be predicted. Now, if you have used ChatGPT, all of you would have seen it doesn't blast out the entire paragraph in one shot. You will see that it looks like somebody's typing it, right? It will say sample, text, LLMs, or each word appears one by one. So this is what is happening in the background at a high level. The neural network just types out, the trained neural network types out. Now, what we are seeing is how the neural network gets trained. So the first time, what happens if you see here, when I put in the four words, the four token sequence into the neural network, fed into the neural network, it goes through various layers. I'll show you how a neural network looks like visually. And it goes through all the nooks and crannies of the neural network. And finally, it prints out the probability of the 100,000 words or tokens of ChatGPT, let's say. All the 100,000 tokens will be given a probability of what can come next. Now, I've just taken a few here, right? So if you see here, 6908 has a probability of 0.5, whereas our target, which is the correct one, 30525, which is the equivalent of the word data sets, is having a probability of 0.4. So now what do? I go and correct 0.4, I increase it to probably 0.45 and reduce 6908 to 0.4. Next time, I again pass a similar chunk of words. Then again correct, again correct. This is how the neural network gets trained. So the yellow box that you see on the left is called the context window when model parlance or train neural network parlance. This context window, right now I've taken four tokens. It can go from 4 to even thousands. I think the latest one, ChatGPT 4.5, has about 100, 100,000 plus, if you can check it out. Or the window can be very long. Okay, so this is how, if you can see this, the neural network slide, this is how a typical neural network looks like in a very simple pictorial way. What you see on the left hand side, you can assume as inputs. What you see on the right hand side, the 4 or 5 circles is the output. Now, let's say, like I showed you previously, we get an output of 6908 instead of 30525. What do? I adjust the neural networks. What do I adjust in the neural networks? Those are called weights. These are called parameters in neural network parlance, and the weights are adjusted. So when you go from left to right in a neural network, it is called a forward pass. And what I then do a back propagation, one of the techniques that is used, and I go back and adjust each of these circles, the weights. Now, intuitively, if I have to tell you how I would look at it, let's say you have a guitar. There are a lot of strings in the guitar, right? There are four strings, right, in the guitar, simple guitar. And then you have at the end of the tail of the end of the guitar, you have few knobs. If you would seen people with all these guitars before they start a concert, they will adjust the knobs at the end of the guitar, right? They will do probably a note of, let's say, a scale or a chord E, and then they'll strike a G, and then they'll see if it sounds like a E or G. First, let's say I strike a G, and it's not sounding like a G note. So I adjust that particular knob. Next, I strike E, and it's not sounding like E. So I adjust that particular knob. Again, I go back to G and change the two knobs. So I keep doing this forward, backward, till for both G and E, I get the right note. This is intuitively what happens in parameter optimization or the backward propagation in neural networks. In mathematical parlance, if you have to ask me, we use adjusting weights and biases, and we use partial differentiation in calculus. So with respect to change in one, what is the change in everything? So you would have seen that symbol dou by dou x. If you look at the mathematical component of neural networks, you'll often see dou by dou x or dou by dou y and all that. So mathematically, you just partially differentiate it, but intuitively, it's a guitar example, you have to get it. So here, if you see in this slide on the right, I have put up a simple mathematical equation. Now, if you look at the mathematical equation of ChatGPT, then it's really huge. So it's going to be very large, and it's not as simple as this. So if you look at this particular equation that I have shown here, you see certain things shown as W10, W20, if you can see the font clearly, and there are certain A's and B's. So the W's are nothing but weights, and the A's and B's, the B is the bias, right? So these weights and biases are adjusted in the forward during the backward pass, like I told you earlier, till the neural network's accuracy is increased. Now, let me show you how a neural network visually looks. I'll just toggle to this particular website, which is very, very intuitive. Uh, you can visualize the LLM. I hope you are able to see the visualization. I'll click on this particular simple one, which is a nano GPT. And we also have GPT-2, then GPT-3, and so on. Let's look at nano GPT. This is how typically it looks like. If the beauty of this site is if you go and click here on a particular thing, you can see actually what is the weight, what is the bias, and each layer. You can see that there are many layers it goes through. You can twist and turn this neural network, the complete forward pass you can study as granular as you want, you can go in and see. I think you should take a look at this and understand more intuitively how this neural networks work. Mainly, I wanted to show you this because if you see on the top, the number of parameters, if you can see, I'll just go back here. In GPT-2, just look at the number of parameters. It is 1,557,000,000. Look at GPT-3, it's 174 billion, 174 billion. So imagine the number, it's mind-boggling. That is the number of parameters which are there in the neural network. And just imagine how that mathematical equation will look like. It has a lot of e power x to the power. What I showed you here is just like alphabets. If you consider English as a language, what I've shown you here is an alphabet of the mathematical equation. So this is how inside the neural network gets trained. So now let's move to the next step. What happened after
So,
that? What happens after that?
sorry.
And
So your
yeah,
PPT is moving just fine, but your video is stuck. Maybe you can just turn off and turn on your video once.
okay, let me try that. Want me to turn off and turn on the camera?
Yeah.
Tina, can you hear me?
I can hear you very well, sir, but I can't see you as yet.
Yeah.
I Yeah, now I can.
Okay. All right. The slide you're able to see now?
Not yet.
Okay, let me do it. Share. Yeah, I think you should be able to see now.
Yes, now, sir.
Okay, how is it now? You're able to see full screen?
Mm, yeah, I can see it full screen now.
And you can
I
hear my
can
voice
see
also.
you as well. Everything is
Okay,
fine,
how
sir.
about
You're
the
good to go.
participants? Can you see some positive responses from them? Are you able to hear me?
Guys, if you can just raise your hands if you're able to see and hear Mr. Kaushik well.
Okay, thank you. I
It's
think I see
audible.
a
Go
lot.
ahead, Kaushik.
Thank you.
Yeah, sure. All right. So when I have a lot of pop-ups here. Okay. Okay. So coming back to just quickly revisiting, sorry about that glitch. So I'll quickly recap. We just gather data from the internet through the data set called Fine Web, and then we do tokenization, and then we do neural network training. Once we do the neural network training, we saw how the forward pass and backward pass work quickly. Then after that, what happens is we have something called uh, decant. Okay, so once we do the forward and backward passes, what happens is we have the trained neural network with us. Now, but in terms of, if you look at it, each data point in the text is in terms of numbers. So there is something called a vector database that you might have heard. In case you've not heard, it's fine. What we do is we humans have this three-dimensional thinking. What is three-dimensional thinking? We live in a 3D world, so we are used to length, breadth, and height. Three dimensions. Any object that you see in the world is a three-dimensional object. Now, what happens if I bring in a fourth dimension? As humans, we can't comprehend fourth dimension, right? So fourth dimension is nothing but mathematically it can be captured, but as humans, we cannot capture the fourth dimension. So how do we bring in an equivalent of that in using something called vectors? And vectors are nothing but if you are aware of matrices, it's a one-dimensional vector. So let's say you have length, breadth, height. It's only three components along the unidimension in the one-dimensional vector. But if I bring in a fourth component, then mathematically it can be captured. We cannot think of four dimensions, but mathematically it can be captured. Let's take the case of a particular bird. A bird can have a flight speed, it can have weight, it can have a color, it can have a habitat. So it keeps going more than three, right? So for each of that, if I have a row in a single column matrix, so that is how the vectors are captured. Now, why am I talking about this? The text that we have is all going to be used as vectors here. The tokenization that we do, why do we have to use vector databases and why it is advantageous? Because let's say I have something called big. I have a word called huge. Then I have something called mountain. So all these denote something big. So if you see in the diagram here, the arrows are spread in multiple directions. So now the word big, huge, mountain, all might be grouped to the large, the arrow directions. They all will be more or less in the similar side. Same way, the nouns will be in one direction. So this is how we capture words as vectors or arrows. Just think of them as arrows and it will make things easier for you. And we do something called a cosine similarity between two words. Let's say I have a word called huge and I have a word called big. The two words, huge and big, almost point in the same direction. So what is the angle between them? If you look at it mathematically, it will be close to zero, or it can be 5 degrees, let's say. And that's why we do a cosine similarity. What does cosine similarity say? Cosine of 0 is 1, which means the vectors are in the same direction. If they are orthogonal, if they are perpendicular, then cosine 90 is 0. That means one word is a noun, the other word is something, an adjective. Or to give you an example, I'm saying one word says large, the other word says small. So these words are in different directions. So this is how vector DBs convert everything numerically and capture them in the vector space intuitively. So this is how we do cosine similarity. So let's move on to the next one. Yeah, I hope you are able to now see the slide. Yeah, this is an important information that I wanted to share with you in terms of LLMs. So what we have here is a group of 8 people that I show who revolutionized what is called LLMs by bringing in something called transformers. And the core to transformers in LLMs, self-attention or attention mechanism. I'll talk more about attention mechanism, but the core to transformers is attention mechanism. So now let's say I'll show you the paper they wrote also so that you can use it for a reference later. I have it. This is a paper that revolutionized things. Attention is all you need. So you can see a couple of familiar names there. Ashish Vaswani. You would have come across this name in quite a few papers. This was released by Google. There is Nikki Parmar. She was a self-trained coder who grew up to this level. So it's a very short paper. It's just 10 pages. And it just brought in something called transformer model. This is the transformer model. I'll talk more about it. Yeah. So let me go back to my. Yeah. So here. This slide is quite important. So I just wanted to spend some time on this to explain to you what is transformer model and what is attention mechanism. But if I get into the details of this in matrices form, then it will take quite some time. It might even need 2-3 hours to explain. So I'll try to make it intuitive and explain to you how these transformers and self-attention mechanism works. Let's say we have all the words I told you are captured as vectors. Now this is called embeddings. On the left, you see a lot of boxes which say embeddings. These embeddings are nothing but one-dimensional vectors. All the words that you see, I have put up a sentence on the top left which says, we have a blue sky. So each of this is an embedding. We is an embedding, have, all this is converted into a unidimensional strip of numbers or vector that I told you. Now we have three key matrices in play in attention mechanism. One is called W sub Q, the other one is W sub K, the other one is W sub V. WQ is a query vector, WK is a key vector, and WV is a value vector. So the important ones here are the query and key matrices. So what happens in query matrix is we take the words in the sentence, we have a blue sky, and then WQ is a weight matrix. You remember I spoke about weights in neural network. This is a huge matrix as usual, having thousands of parameters. The weight matrix, the embedding vector is multiplied by the weight matrix WQ, and we get a query vector. The same way the embedding matrix is multiplied by the key vector WK or weight matrix, and then we get a key vector. And similar for the value vector. Now what we do is the query vector, without getting into much details, intuitively what it says is, let's say the query vector here is sky. Sky, the word sky will say, I am looking for an adjective. Is there an adjective before me or near me? It's looking for an adjective. Blue sky. If I just say sky, it is a noun, it's a word. But when I say blue sky, it qualifies the word sky. So in English, it says the definition is an adjective. Now, when I say sky, the word sky as a query vector will look for any adjectives near that. And then what does blue do? Blue gets captured in the WK or the key matrix. And what do those keys tell? The keys shout out loud that I am an adjective, I am an adjective. So all these words are captured in that form. The sky is captured this way. When you see a sky and a blue, then these two are pointed in the same direction, or there is a shift that happens in the vector space. And they both are aligned together. Blue will be in some adjective space, sky will be in another noun space. But then together also they form a space which says qualifying a noun, blue sky. So you'll have cloudy sky, blue sky. So as it reads tons of text in the internet, it'll come across blue sky multiple times, cloudy sky multiple times. And all these are captured in this way. So this is what happens in the query vector and key vector. On the right side, if you can see, there's a green arrow, which says we do a dot product. The similarity that I told you earlier, the cosine similarity. And both are similar, then the attention score is very high. So the blue sky gets high scores. So in the sentence, we have a blue sky, the model attends to blue and sky. That is why it's called attention mechanism. That is a core concept of attention mechanism. Now, mathematically, if you want, you see an equation at the top which says attention of q, comma k, comma v, which equals softmax of q k power t by root k. I'll quickly tell you what it is. You see the q vector, the query vector, and the key vector. The query vector and the key vector is transposed. If you understand the matrices and determinants of mathematics, if you can recollect, the key vector is transposed so that it can be multiplied by the query vector. And to reduce numerically, scale it numerically, it is divided by the square root of the dimensions of the key vector so that you get a scale of numbers. That entire thing is passed through a function called softmax function, which results in probabilities. Let's keep it at that for now. It results in a strip of probabilities for all these words. Now, all these probabilities, like I told you initially, for this entire text that is passed through the context window of pre-training or the embeddings, gets a probability score, and that is multiplied, weighted with the values. The values are the actual words. That's why it's finally multiplied with V. And this results in the attention weights. This attention weights give relevance. This is called self-attention mechanism. So we have a blue sky. In this, blue and sky get high attention weights. So this is the core behind attention mechanism, or the paper that I showed you written by Vaswani, Parmar and all those people. So I just wanted to spend some time on this. So we'll move on to the next step. Before that, I just wanted to give you a hint on how these things actually happen in the real world. We have this company called NVIDIA, which all know the share skyrocketed recently. And NVIDIA has processors. What you see here is a H100 GPU picture. So if I put four of these together, it's called a unit, and I put multiple such units and I form a rack. Multiple such racks form a farm. Using this, Elon Musk has created a gigafactory of compute. You can Google about it and see he has created a gigafactory of compute, which has huge, unimaginable processing power. And that is how we are able to make these models so intelligent and so on. So to summarize the complete pre-training, first we process the internet, we then do tokenization, we do neural network training, which includes, of course, the transformer mechanism or the attention mechanism. This entire thing roughly takes, if you ask me, about 3 months to do with all this processing power and all that. Now it might have become faster. And what is the final outcome of this pre-training? The internet. We get a base model, which is nothing but an internet document simulator. So we have the entire internet as a document simulated. You can understand it that way intuitively. Now, if we move to the next step, which is post-training. So we saw pre-training. Now we got the entire internet as a document. What do we do with that? Now, if I have all words, imagine that clear blue sky, that what do I do with that? When somebody, like, say, you ask me a question in Chat GPT, let's say I'm Chat GPT, you ask me a question, what is the solution for this? I cannot have a chunk of sentences and be able to, I should be trained on conversations. So conversations is the key for post-training. So, and how are these sets formed? They are formed by human labelers. You see there in purple, I've highlighted, a question is asked, what is 10 times 10? The human labeler will see, what will the human labeler do? He will understand the context and explain when you multiply a number by another number, this happens, and so the answer is 100. So like this, people sit and human labelers sit and create conversations and prompts and conversations. And I'll show you the paper on that and share it with you later so that you can go through how actually this is done in that high quality paper. It is explained. This does not take 3 months, but it takes several hours, definitely. So let's go a bit deeper and see how these conversation data sets are formed, like how the fine web data set initially for pre-training. For post-training, conversation data sets are formed. So I'll just show you the paper which explains this so that you can clearly understand. So this is the one. Now, if you look at this, if you are able to see this paper clearly, here you can see that there's a lot of prompting that has happened. Like, let me take this use case as brainstorming. List 5 ideas of how to regain enthusiasm for my career. Somebody is asking this prompt. Now there are a team of people who are hired by all these companies. Let's say Meta develops Llama, ChatGPT, OpenAI. They hire people, and probably from places like Upgrad, you can read in the paper, and or other organizations. And the same person or a group of other people sit and answer all these prompts. So you can see here, I'll show you more examples. What are the 10 science fiction books that I should read? That's the question. Now, another person or same person will read about it and answer that. This is how conversation data sets are created. Because initially you need raw data to train the neural network, train the transformer. So it keeps creating such raw data text, and there are clear instructions also. If you can see in this page, they have clearly stated how labeler selection is done. It is selected from Upwork. Sorry, I said Upgrad. They selected people from Upwork and or source from Scale AI. And these people sit and do, and they are given clear instructions as to how they are supposed to say, create prompts and how they are supposed to design responses. Now, this is the effort that has gone through. But then now we have enough data for that. So we don't reinvent the wheel, but then what is already there is being used. So I'll also show you another example of Open Assist, which will give you more clarity on this. Yeah, here, if you can see my screen, on the bottom right, you can see something which is light colored, which says, can you write a short introduction about the relevance of the term monopsony in economics? That's a question. This is created by a prompter. And the answer is also given by a human, which says monopsony refers to market structure where there is only. So this way, you can go to this website. This is again Hugging Face. You can go to DataSys. There's an open assistant which helps you get data for you to practice and use. So now, like I mentioned earlier, these conversation sets need not start from zero. So they are already there, and then they have these sets created already. They have developed this, and you don't have to reinvent most of it. It's already done. So if you look at it, when you type something in ChatGPT, I'm taking ChatGPT as an example because it's very common. The response that is coming from ChatGPT is just statistically imitating these labelers. The labelers that you saw who created all these thousands of conversation data sets. Question, response, question, response. This is the data set. So all these data sets are being understood by the neural network or transformer that is trained, and statistically it is being imitated by ChatGPT. So, for example, if the ChatGPT does not knows the answer to a question, or if it has it in the post-training data set, we are going through post-training now. If I see create a conversation data set, and the question that you or I asked to ChatGPT is available in the post-training data set, then it immediately replicates the answer. If it is not available in the data set, then it goes to its pre-training knowledge, which we discussed earlier, and then finds out the answer and comes back. Now, if it's RAG or retrieval augmented generation, which you might have heard of, then it's pointed to a particular database for support to retrieve data. Or if you tell the chat GPT sometimes in the prompt, use a tool or use whatever you like, then it goes and fetches data from particular resource and gets it. So intuitively, if you have to understand this, what happens is, let's say you are doing your final examination in your college and you are trying to recollect or revise your question. Suppose there is a tough topic, you vaguely remember it, but you don't know the answer for that. Then what you do is you go back, revise, train yourself, and come back and answer. This is similar. Intuitively, this is what ChatGPT and other models do. If they can't do that, they get into an issue called hallucinations. That's what I'm going to talk about now. So hallucinations is nothing but LLMs making up text. Suppose you're asked a question in the exam. You have studied it long back 2 months ago. So you remember a couple of words, but it's a, let's say, a essay type of question. So you try to make up something with those 2 words, right? To get some marks, like we call in school, you get step marks, you write something. That is typical hallucination. So LLMs also hallucinate. Of course, the ones that are released now, like DeepSeek, is excellent. I think it more or less doesn't hallucinate from whatever I have tried, but still there is road for him. Maybe the questions to make it hallucinate need to be very tough. Now, earlier models, if you ask simple questions, you can make them hallucinate, but now the models are getting strong. So how do we prevent hallucinations? Couple of ideas are there. You can take a paragraph, you can generate the answer, try it out, if try it out in another model. Now you have llama, you have meta, you have so many things, right, from meta, and you have ChatGPT. So if the other model cannot answer that, then you come back and say, this model has to say I don't know. It should not hallucinate. It should say I don't know. So you give that answer, then the neural network neuron which fired on a low probability to hallucinate will be corrected to say I don't know. So then the model becomes more smarter. If it doesn't know, it clearly says, I don't know. And now the models have become more smarter. They not only say, I don't know. I'll show you another example to overcome that. We can put tags like what you see in the screen, like search tags in front and back of the question. If the model doesn't know, immediately tag it with this. So what happens? It goes to the resource or the internet, searches for that answer, and comes back. So you sometimes you prompt the model to say use a tool or use code. Now you don't have to do that also. It's getting further stronger. It goes, searches, and then comes back with this particular answer that's needed. Now let me put a question to all of you. If you're maybe you can think for a few seconds and then tell me. I've highlighted two questions in this. Let's say, okay, two answers in this. You don't worry about what is there in that. It's a physics question. So simple Newton's second law. There is a mass of 20 kg moving at acceleration 2 meter per second square. So F equals ma. 20 times 2 is 40 Newton is the answer. So now there are two ways to put out this answer by a model. If I'm developing a model, I can tell first the answer is 40 Newton. Then I can give the explanation, Newton's second law, so and so, so blah. Or I can first give the explanation and then give the answer is 40 Newton. Now, which of this do you think is computationally more intensive or better for the model or bad for the model? You can take a few seconds to think about it. Okay. So the answer number one is not correct approach because it's computationally very intensive. I'll tell you why. Because it first says the answer is 40 Newton. To arrive at that number 40, that particular token has gone through all the calculation and explanation of Newton's second law, F equals ma 20 times 2. Everything is embedded into that 40. Behind that token 40 or that symbol 40 is all the intense calculation. Now, this is for the straightforward question that I asked. Now, let's say I ask a very tough question. And imagine I say, you can try out this prompt in ChatGPT. If you have parallelly opened it, you can try. Just tell ChatGPT a complex, a hard question, and then say, give me the answer. Don't give me anything else. Just force it. You will see that it struggles, or take an older version of ChatGPT and do. By now, it might have improved. So it'll struggle, it'll think for some time, and then it'll sometimes it gives wrong answers also. So it's not completely reliable in some cases. But now the models, DeepSeek and all, is a thinking model. I'll show you a bit of DeepSeek also, time permits later. So the answer number one is that's why wrong. If you see the answer number two, it first gives the explanation and then gives the answer. The answer is 40 Newton. So the load is distributed across tokens. Because models need tokens to think. If you are going to overload a particular token, computationally make it intensive, and a single forward pass becomes very intensive and becomes a challenge for the model. So the same thing, I have typed out one more question. You can try it out at your own leisure. So what I was trying to say here is, like I mentioned earlier, the single forward pass across the neural network makes it computationally intensive. So we need more tokens. And let's try this out once quickly, maybe. I will show you the other drawback of some of the models. Let me go to Chat GPT if I have it open here. Yeah, I have this dot count. If you can see my screen, this is Chat GPT. I have asked Chat GPT to count the number of dots in the string. I had actually put up 181 dots in the string. And it is learned from a previous question smartly, and it's used Python code also, done a string count, string.count. But it is fed the dots as a string, and the string variable has a function called count, you all know. So it did string.count, and still it got it wrong as 165. So models are still, maybe once it will get it right. Once it will say 181. If you just try it out 5 times or 8 times, you will get 3 wrong answers and 5 right answers. So still, in terms of counting, the models are not strong. Any guesses as to why? I'll go back to the PPT. The reason is, initially when I saw the tick tokenizer, the LL was one color. I told you to remember, and I'll touch upon it later. And MS was in another color. LLMS, the MS was in a different color. LL was in a different color, right? So that way, 10 dots is taken as one token by the model, and 25 dots is taken as another token. This causes discrepancy. That's why models are sometimes not great with counting and also not good with spellings. If you ask how many U's are there, umbrella, it may tell. But if you ask what is the third letter after the fifth letter from the right and how many U's are there, and guess something like that, then you will see that sometimes the models struggle. So these are certain things which the models are still not reliable. So just to quickly summarize the post-training, the difference between post-training and pre-training is that it's more or less the same sequence that we go through. But instead of the internet data in pre-training, here we do conversation data, which is built by human labelers. And there are millions of conversations between human and assistant is fed into the system. And this technically is called supervised fine-tuning. Why is it supervised? We fine-tune it, but human labelers are involved, and we already have the labels, which is typical case of supervised learning algorithms. So the last one that I wanted to touch is, we have seen pre-training, we have seen data from the net converted into base model, taken through post-training, the attention mechanism and conversation-based data set, and so on and so forth. That's the big picture now. Now, finally, what fine-tunes it further is reinforcement learning. There is a certain limitation to it, though. Reinforcement learning fine-tunes it. Reinforcement learning is nothing but, let me see if I have captured it here. Yeah. Let's say I ask a question, 10 times I ask similar question or the same question. and 4 times the model gets it right, 6 times it gets it wrong. So I will take the 4 questions times it got it right, and I will score them in probabilistically or some scoring mechanism. I'll score those 4 and say which is the strongest and best out of the 4. What I will do then, I will see how the model traversed across the neural network, and I will take those parameter values and optimizations. And on that particular solution, I will train the model again. So I reinforce the model, reinforce the training. And by repeating this again, we will tune the parameters according to the correct solution sequence. I remove the wrong answers, I take the correct answers, take the strongest of them, and then parameterize according to that in the neural network. So that way, it is reinforced. The neural network is reinforced. And by doing this, DeepSeek published a paper recently, I think few months ago. I have that paper. I can share that with you. You should read that paper because it's from top quality and the best sources. Uh, if you see, there are 2 lines here, blue and these are by different models. And you see as the number of the reinforcement model gets into the act, the accuracy keeps increasing. The y-axis is the accuracy. The accuracy keeps increasing. So, and the other important point to note here is that as the number of steps increase, you see the shaded lines also going up and down. There's a dark line that you can see, and there is also a blue light shade that goes up and down. That denotes the average length per response in the y-axis, which is nothing but the context window or the token. The use. I remember I said initially I took an example of 4 numbers, and then I told you it can be in thousands of numbers. So that number from 4 increases to thousands. So as the average length per response increases, you see that the model also becomes more effective, because the more effective the training becomes. So these information you can find in the DeepSeek paper, which was recently, you can search for DeepSeek reinforcement learning paper. It is available on the internet publicly. So now the model also starts thinking finally. After doing all this, the model also starts thinking. I'll just show you an example of that before we close. But there is a slight warning about reinforcement learning. Reinforcement learning, there are 2 things. One is there's a concrete output in some cases, like the physics question I asked, there's a concrete output. Suppose there is no concrete numerical output. I asked the chat GPT to write a poem or write a joke. Tell me a joke about something, about the building or something like that. Then it will start generating randomly till it arrives at a laughter scenario where humans can laugh at it. But if you keep repeating this again and again, it doesn't get better. It will just repeat some words like I, that kind of outputs you will start getting. So there is a limit. So the reinforcement learning fine tunes the model to some extent. It goes up the graph, stays flat, and then falls down. So you can use it only to certain, but there's a lot of research going on even today in that area. So you can study more about reinforcement learning if you want to go deeper into it, right? So, and there is this website called together.ai, and it is wonderful site for you to see there a lot of models are shown there and how the models think. Let me go to that site and then I'll show you quickly. Hope I have it. Yeah, this is the together.ai. Let me quickly ask it a question. If I carry a weight of 5 kg over 20 meters, what is the work done? Now, this is a typical question in physics where you will think that if I carry a weight of 5 kg over 20 meters, of course, there is work done. Yeah, biologically, chemically, your arms pain and you walk and you do work. But in terms of physics, a force has to be applied over a distance, then only work is done. So you will see the answer. Let's see what together.ai says. See the way it is thinking, like how we think. Look at, for this simple question, how much text it has printed out. What is happening is like how we humans think, it starts thinking. So it is telling, okay, if I carry, then this is the weight, this. So in great detail, sometimes it's even so elaborate that you can write an essay with that. It still has not stopped. So you can try out how models think using after this fine tuning RL and all, they think it keeps going so on. It's going on. So I just wanted to share that with you, how amazing these models have become. See, so the answer is, you just saw that above, that the answer is zero joules, right? So I will just show, go up and so for work done is zero, which is correct, because in physics, if you force is applied over a distance in the direction of the movement of the object, you apply F dot D, which is FD cosine theta, and in the angle you calculate. So in this case, you just carry a weight over a distance. The force doesn't act over a distance. Of course, gravity acts, but that doesn't pull the object up or down. So that's why the answer is zero. And it is taught beautifully and given an elaborate answer. So this is the depth to which the models can think nowadays. So you can try out all these things, and you can also simulate these models. If sometimes what happens is, when people the reinforcement learning, people are used to give human feedback, and that also can be simulated. Let's say I have to give 10 prompts, and 10 people have to roll out 10 times 10, 100 people effort is needed. Imagine thousands, then one person has to do it 10,000 times, or the 10,000 people have to do it, 1,000 people have to do it 10 times. It's a huge task. So what we do is, we take the human responses, and again we train a new separate neural network outside of the attention, the neural network of the model, which is called a reward model, as I have highlighted there within quotes. That reward model is a neural network which simulates humans, right? So then there are certain limitations to that. So that is another area which is coming up a lot, which is reinforcement learning based on human feedback. So this also is connected to generative adversarial networks, and how we generate and we train the models. For example, if you're uh, training on a poem, then as humans we can only uh, discriminate. This poem is better than this, or this joke is better than this. But I cannot generate a joke. To generate a joke is more difficult. So we ask humans to only discriminate. Generative adversarial network, there is a generator and a discriminator. Two neural networks compete with each other. That is the core of GAN, generative adversarial networks. So we in this case, we ask the humans to discriminate, because discrimination, commenting about somebody, is always easier than generating something positive. Just for a lighter vein, I said that. But this is how we do it, and this is how the RLHF happens. You can, this is also an upcoming area where a lot of research is happening. Now the positive of RLHF is that, like I told you, we do the generation, we don't do the generation part. The negative is that if we do that, after a while, like I told you, the improvement happens, it remains flat and it drops off. We start getting nonsensical outputs after a while. So you have to see and balance it out for a certain level only. So that's one. So this is my final slide on a couple of examples on industry use cases. So there are a lot of areas where it is applied, in medical, in drug discovery, and all those. Two very common ones are sentiment analysis and content generation. So it's a very powerful tool, because if you're working in the retail industry and you're doing social media analytics, then you can do apply graph theory and do sentiment analysis, and that can be combined with LLMs to increase the power. That sentiment analysis can be powered to do content generation or marketing content, fine-tuned to each prospective customer. So that is a power you can generate using LLMs. And the other one, of course, is virtual assistants. The simple form is chatbots you would have seen often being used. They are becoming very effective. Like I told about Elon Musk earlier, Gigafactory of Compute, he is building something called Grok, GROK, which is, I think, a chatbot. So those are the huge industry applications, to name a few. So, so that's all I had from my side. So thank you so much. And if there are any quick questions, I would like to take them up now.
Thank you so much, sir. If there are any questions, those who haven't dropped it, please do so, and you can do it in the Q&A section.
Tina, am I audible now?
Yes, sir.
Yeah. So
So I have one interesting question. What's the role of ethics in building and using LLMs? Can bias be removed completely? How do AI models handle sensitivity or culturally specific content responsibly?
oh, very good question. So in terms of the whole base of this entire machine learning AI and all, it starts with bias and variance. So whoever has asked that is a very good and basic question. So if you have any data, the challenge that we had in have in world is the availability of data, limited availability of data in certain contexts, and the variability of data. These are very important aspects to balance. So ethics is the most important thing in when it comes to LLMs, and that is why we have so many filters and all these clear instructions being given to human labelers. So to answer your question short, if we cannot guarantee that it is completely removed, the bias is even I think there was an incident when Google launched their Bard, I think, few months ago. Something happened. You can Google about it and see what happened there. And the answers were very biased. So even after training on billions of tokens, this happened. So we may not be able to completely remove, but yes, by bringing in ethics, we can control, like I said, how to stop models from hallucinating. So those kind of hooks and stops and blocks we can put in and improve, definitely.
Thank you, sir. I have one more, which is more related to career. So it's a very basic one. What kind of jobs are emerging because of LLMs and AI? And I'll club one more question along with it. How good should I be at math or coding to get into AI and machine learning? Where should I begin as a student?
Okay, two parts question. One is job related, the other math related. So see, in terms of jobs, whatever is being automated, for example, LLM or AI can auto. If you are in a job which can be automated, then yeah, that might be replaced with AI, you can say. But then if you are someone who is creating stuff, which two ways to look at it, you can either be in that research area which I showed the research papers where you can create stuff which helps or aids AI development and all that. That is one extreme. The other extreme is you can use all these models and LLMs in your day-to-day application or your job and your area of work. So that way you are tied to AI and LLM where whichever way you look at it. Either you create it or you utilize. You should become a consumer or a creator. And as far as math goes, if you are going into the research area, if you want to improve on an algorithm or the model, then definitely math is the key. Without math, like even if I showed you the transformer, the self-attention model is completely based on math. So there are areas like linear algebra, probability and stats, and yeah, these are two, three areas that you can definitely you have to be strong in if you want to go into the research oriented work.
Thank you so much, sir. Since we are also running short of time,
Yeah,
we'll pause here and maybe if there are more questions and if people send it in to us later, we'll reach back to you and get those answers to them somehow. So we'd love to hear your feedback, everyone who's participated. I request you all to please fill the feedback form. You will either see it pop up in the Q&A section right now, or we'll also send out an email where you can fill up your feedback about this session. And thank you so much for being here with us. Thank you so much, Mr. Kaushik, for all of your insights. I'm sure everyone had so much to take away from your session. And once again, thank you all for being a part of this meaningful conversation. And we look forward to seeing you soon again next week. Take care and have a great evening.
thank you.